So first section on chapter 4.1 is going to be about angles and radian measure. So again, most of this you guys will have seen before. It's just going to be a quick recap of stuff you've done before, just so that we can make sure we're all speaking the same language. So we'll go over some terms you've seen before, radian angles and what that means, and then we'll talk about how to convert in between degrees and angles. And then the last three, these last two will be formulas, and coterminal angles are pretty easy as well. So it's all pretty straightforward. It's just going to be some notes and writing down for you guys. So first thing, new terms, or not even new terms really, when we just talk about these terms, you've seen them all before. Initial side is obviously the starting side, terminal side is where we end. And when we talk about rotation of an angle, counterclockwise is always going to be our positive rotation, and clockwise will be our negative. Angle types you've seen before: acute less than 90, obtuse between 90 and 180. Right is 90 degrees, and a straight angle is 180 degrees. So nothing on this page would I expect to be new to you, but it's important that you make sure you remember them, and in particular when we're drawing angles, the difference between counterclockwise and clockwise, positive and negative. Now, when we talk about how many radians are in these degrees, so radians is essentially the same idea in degrees, it's just a different way to measure them. So if you think about terms of distances, we talk about yards in this country. In Europe, they use meters. Now, essentially, it's the same idea. They're just using a different standard to measure them. Same idea with these ones. Now, these are three of the bigger ones. There's 360, 360, a complete turn is going to be 2 pi. 180 degrees then is half of that, so that would be pi. And then 90, half of that, we write as pi over 2. And now every time we work with radians in this, we're going to be dealing with pi, and we're not going to approximate pi as 3.14. We're going to leave everything in terms of pi, meaning just don't multiply by pi by 3.14. Work with all the other numbers and simplify them first. And now when we convert between degrees and radians, to go from degrees to radians, we multiply by pi over 180, and then we do the reciprocal when we're doing radians to degrees, multiply by 180 over pi. And so those are two pieces that you're going to need to remember. Remember, when you're going to radians, pi should be on top. When you're going to degrees, 180 should be on top, or the degrees. So a couple examples here. If we want to convert from degrees to radians, we're going to multiply by pi over 180. And remember, we don't want to multiply by 3.14. So we'd have 42 pi over 180, and then we're going to simplify that. And we should get 7 pi over 30. Okay, that would be our simplified fraction. Likewise, if we multiply this by pi over 180, we're going to get negative 259 pi over 180, and that actually does not simplify anymore, so this is how we would leave it. Okay, big thing for degrees to radians is just multiplying by pi over 180. Now, vice versa, when you're going from radians to degrees, we're going to multiply by 180 over pi. And what should happen here pretty much every time is your pi's should cancel out. So we have 180 over 6, which is going to give us 30 degrees. Okay, likewise, times 180 over pi, your pi's should cancel out. So if we multiply that, 4 over 7 times 180, you should get 102.9 degrees. 102.9 degrees. So big thing on this one. Radians to degrees, 180 over pi. And then we have what are called coterminal angles. That just means angles that have the same initial and terminus size but different measures. So if you think about on our xy axis what that would look like, we could have one angle here, and that could be, let's say, 45 degrees. Now the way that's different is if an angle starts and goes all the way around in a complete circle and then ends on that same terminal side, this one then, so 45 plus 360, would be 405 degrees. So to create a coterminal angle, or to figure out what a coterminal angle is, we're just going to add or subtract multiples of 360 or pi, depending on if you're given degrees or radians. So when it is already more than 360, we subtract 360 to find it between 0 and 360, and so 420 minus 360 is going to give us a coterminal angle of 60 degrees. Okay, now when it's negative, if we want a positive version, we're going to add 360. So negative 279 plus 360 is going to give us 81 degrees. Okay, now there could be times where you have to multiply 360 or add 360 more than once, or subtract 360 more than once, until you get it less than 360. So second to last thing, our formula for arc length is going to be radius times theta, where r is your radius and theta is the angle, the central angle in terms of radians. Okay, so what that would look like, if I draw a circle here, and then we could have our radius and another radius. This would be our r, and this, our central angle, would be theta. So this piece right here is going to be your arc length. That's what we're solving for. Okay, so that's your formula. So if we use this, remember S equals R times theta. If our radius is 10 and our central angle is 120 given to us in this problem, then our arc length would simply be multiplying those two, 1,200. Okay, and its length, so that's going to be 1,200 inches, don't forget. That would be our arc length. Simple enough, straightforward. And then we're going to have linear speed. So linear speed is the speed of a point in a circular motion, and this is our symbol, and it's going to be S over t, where remember S is arc length, and t, like normal, is time. So we figure out, in other words, the distance divided by the time gives us our speed. Okay, we also then have angular speed, so the speed at which it is actually turning, and that's going to give us our angle over our time, and that gives us our angular speed again. So how far it turns by how fast it turns. Okay, so distance over time, again, same idea. Now if we use our formula for arc length, which remember is S equals R theta, and we plug that in to the formula for linear speed, which if we go back, remember was S over t. So S over t would now be R theta over t, and using that combined with our angular speed, solving for theta, okay, so to solve this for theta, I'd end up with the radius times the angular speed. Okay, so in other words, this just says that our linear speed equals our radius times our angular speed. Okay, and if we have questions about that, if we're not quite sure about that, I'll be happy to go over that in class. I kind of covered it quickly because we have a lot to go over. And this can be a little bit confusing just seeing all these formulas jumbled together. We'll go over that in class tomorrow to make sure we all understand what I'm talking about here. Make sure though that you do have that formula down. Okay, and then this is going to be your challenge problem. Okay, so you're going to solve this on a half sheet and turn in at the beginning of class. Okay, so a turbine used to generate electricity has blades that are 10 feet in length. The propeller is rotating at 4 revolutions per second. So if you're talking about rotation and speed, think about what that is actually giving you. And find the linear speed in feet per second of the tips of the blade. So that tells you something important as well. And so that is it for this lesson. You've got your challenge problem for tomorrow. We went over all of these things. Probably the most important one that you're going to need is converting between degrees and radians. So remember, to get degrees, it's 180 over pi, and to get radians, it's pi over 180. Okay, we'll see you next time.